propulsion. In the diagram, three stages in connection with the motion of rocket have been shown. M0 is the initial mass of the rocket, and rocket is moving upwards with an initial velocity v0 at instant t equal to 0. At instant of time t equal to 0, rocket is moving in vertically upward direction with an initial velocity v0, and m0 is the initial mass of the rocket at t equal to 0. At instant of time t equal to 0, rocket is moving with initial velocity v0, and at instant t equal to t, small amount of exhaust gases are ejected from the rocket. Small amount of exhaust gases are ejected from the rocket. And dmi is the small mass, is the mass of small amount of exhaust gases. dmi is the initial mass of small amount of exhaust gases which are ejected in vertically downward direction from the rocket with the initial velocity vgi, with the initial velocity vgi, and this is the exhaust gases which is in small amount exhaust gases that are released from the rocket in vertically downward direction with an initial velocity vgi, and mass of the rocket increases to m. Small m is the mass of the rocket, and mass decreases to m and velocity increases to v. In this case, mass of the rocket decreases to m, and velocity of the rocket increases to v by keeping the linear momentum constant. And at instant of time t equal t plus dt, where dt is small interval of time, large amount of exhaust gases are ejected from the rocket in vertically downward direction in this way. In vertically downward direction, large amount of exhaust gases are released with an initial with a velocity vg, v subscript g. This is the exhaust gases which are released from the rocket in vertically downward direction, and dm will be the amount, will be the mass of the exhaust gases, and exhaust gases are released with an with the velocity vg, with the velocity vg. Velocity of the exhaust gases in vertically downward direction is vg. In vertically downward direction is vg. vg is a, and rocket moves with greater velocity v plus dv, and mass of the rocket decreases to m minus dm. Also at instant t equal to t, dmi will be approximately equal 0 because small amount of exhaust gases are ejected from the rocket at instant of time t equal to t. Now let m0 is the initial mass. m0 is the initial mass of the rocket. m0 is the initial mass of the rocket, including its fuel, initial mass of the rocket including its fuel, including that of its fuel at instant of time t equal to 0. Initial mass of the rocket including that of its fuel at instant of time t equal to 0. During the flight of the rocket in vertically upward direction. M0 equal initial mass of the rocket including that of its fuel at instant t equal to 0 during the flight of the rocket directed vertically upward direction. Directed vertically upward direction. V0 is the initial velocity of the rocket. V0 is equal initial velocity of the rocket. Initial velocity of the rocket at the instant t equal to 0. Initial velocity of the rocket in vertically upward direction at instant t equal to 0 second. At instant t equal to 0 second. Here we can make a correction. Here we can write let at t equal to 0, comma, m0 is initial mass and v0 is initial velocity of the rocket. Similarly, at t equal to t, at instant of time t equal to t, at instant t equal to t, dmi is the initial mass or mass of the rocket, mass of the exhaust gases, mass of exhaust gases, mass of exhaust gases which are ejected, or which are escaping with an initial velocity vgi. dmi equal mass of exhaust gases which are escaping with an initial velocity vgi. V equal, or v is the velocity acquired by the rocket, at that instant, and m is the mass, reduced mass of the rocket, because m is less than m0, mass of rocket at that instant, mass of rocket at that instant. Also, after very small interval of time dt, that means at the instant t equal t plus dt, now at instant t plus dt, comma, large amount of exhaust gases are released from the rocket with a velocity vg, and dm will be the mass of exhaust gases. dm equal mass of exhaust gases, mass of exhaust gases mass of exhaust gases that escape from the rocket with the velocity vg, with the velocity vg, v subscript g, with a velocity v subscript g. vg is the velocity of exhaust gases uh, which are ejected from the rocket in vertically downward direction. dv is the increase in velocity of the rocket or corresponding increase in velocity of the rocket in vertically upward direction. dv equal corresponding increase in velocity of the rocket, corresponding increase in velocity of the rocket due to ejection of exhaust gases. Now in the diagram we can explain the motion of the rocket in 3 stages. At instant t equal to 0, rocket moves with an initial velocity v0 in vertically upward direction, and m0 is the initial mass of the rocket. And at instant, and no exhaust gases are released from the rocket at the initial instant t equal to 0. Now at the instant t equal to t, small amount of exhaust gases are released from the rocket in vertically downward direction with the initial velocity vgi, and vgi is the initial velocity of the exhaust gases, and dmi is a very small amount of mass of exhaust gases, dmi approximately equal to 0, and mass of the rocket decreases to m, therefore m less than m0, but velocity increases to v because mass decreases and velocity increases by keeping the linear momentum of the rocket constant. And after very small interval of time dt, that means at instant t equal to t plus dt, large amount of exhaust gases are ejected in vertically downward direction. Exhaust gases are ejected in this direction, means in vertically downward direction. dm is the mass of exhaust gases with an initial with the velocity vgi. So this is the exhaust gases which are ejected from the rocket with a velocity vg, and mass of the rocket decreases to m minus dm, and rocket will be moving upwards with greater velocity v plus dv. So dv is the corresponding increase in velocity of the rocket at instant t equal to t plus dt. Now we can draw the diagram of rocket here at instant t equal to t, and at instant t equal to t plus dt. According to the principle of conservation of linear momentum, according to the principle of conservation of linear momentum, we get total initial linear momentum of rocket and exhaust gases will be equal to the total final linear momentum of the rocket and the exhaust gases. So mv plus dmi vg, dmi minus vgi will be equal, here mv is the initial linear momentum of the rocket and dmi minus vg is the initial linear momentum of the exhaust gases, is equal to m minus dm into v plus dv, which is the initial linear momentum of the rocket plus dm into minus vg, which is the final linear momentum of the exhaust gases. Here at instant t equal to t, at t equal to t, mass of the rocket is m and velocity of the rocket in upward direction is v. So m dot v is the initial linear momentum of the rocket, and exhaust gases will be, rocket will be moving in upward direction with velocity v, and exhaust gases will be released with a velocity vg and in vertically downward direction. So dmi into minus vg is the initial linear momentum of exhaust gases. So we get mv plus dmi minus vg as the total initial linear momentum, and final linear momentum of the rocket in vertically upward direction is m minus dm into v plus dv, and dm into minus vg is the final linear momentum of the exhaust gases. In this case, v plus dv is the final velocity of the rocket, which is in the upward direction, and exhaust gases, these are exhaust gases which are released in vertically downward direction with velocity vg in vertically downward direction. That's why vg is negative with respect to v plus dv. mv plus dmi vgi minus dmi vgi is equal mv mdv vdm minus dmdv minus vgdm minus vgdm. On the left hand side we should have dmi into vgi, or comma 0 dmi it should be vgi or comma minus 0 comma minus vgi dmi equal mv dv, because mv and mv will cancel out, mv dv minus vdm minus dm dv minus vgdm. dm is small decrease in mass of the rocket or mass of exhaust gases released. 0 equal mvdv minus vdm v plus vg, dm is taken common, minus dm dot dv. In this case, small amount of exhaust gases are released initially. That's why dmi approx equals 0. So under bracket what we can write, dmi approx equals 0, because initially small amount of exhaust gases are released from the rocket. That's why dmi equal to 0. That is applied in the last line. Or we can erase this part and we can write down the logic why minus vgi dmi is 0. Here we can write as small amount of exhaust gases, small amount of exhaust gases are ejected at instant t equal to t, comma, mass of the exhaust gases at that instant, that is dmi, can be assumed as approximately equal to 0. At instant t equal to t, at instant t equal to small amount of exhaust gases are released from the rocket. This is the small amount of exhaust gases which are released or ejected from the rocket in vertically downward direction. That's why initial mass, that is dmi, will be approximately equal to 0. dmi will be approximately equal to 0 because small amount of exhaust gases are ejected from the rocket. But at instant t equal to t plus dt, large amount of exhaust gases are released. That's why mass will be dm. Mass of exhaust gases will be dm. Large amount of exhaust gases are released at instant t plus dt. That's why dm will not be 0, but dmi approximately equal to 0. Or comma 0 equal or comma m dv 0 equal m dv minus v plus vg into dm minus 0. Here dm and dv are small amount of mass. Dm is small decrease in mass of the rocket and dv is small increase in volume of the increase in velocity of the rocket. As dm and dv are both very small, so that's why product of two very small quantities will be approximately equal to 0. Hence dm dot dv approximately equal 0 or mdv equal v minus v plus vg plus v plus vg dm. mdv equal plus under bracket v plus vg bracket close into dm. Or comma dv equal, that is increase in volume, increase in velocity of the rocket in small interval of time dt is v plus vg divided by small m. M is the final mass of the rocket into dm. This is the corresponding increase in volume, increase in velocity of the rocket. Increase in velocity of the rocket, dm is equal v plus vg divided by m into dm. dm is decrease in mass of the rocket, or dm is the mass of exhaust gases, but dv is increase in velocity of the rocket. This is equation 1 and that is equation 2. Now the relative velocity of the exhaust gases with respect to the rocket, relative velocity of exhaust gases, relative velocity of exhaust gases with respect to the rocket is, with respect to the rocket is vector u equal vector vg minus vector v, because relative velocity is the difference in velocities of exhaust gases and rocket. Therefore vector u equal vector vg plus minus vector v. That means we have to add uh, vector vg, means velocity of exhaust gases, with the negative velocity of the rocket. That's why mod vector u is equal to mod vector vg square plus mod minus vector v square plus 2 mod vector vg mod minus vector v cos 180 degree minus theta, cos 180 degree minus theta. We can draw the diagram again to denote the angle between velocity of exhaust gases, that is vg, and the velocity of the rocket. This is the rocket. Rocket is moving upwards with velocity v, and this is the rocket, and exhaust gases are ejected from the rocket in vertically downward direction with the velocity vg. So that's why vg and v are opposite to each other. That's why theta equal to 180 degree, means angle between the direction of vg and v is 180 degree. vg is in downward direction and velocity of the rocket, that is v, is in upward direction. That's why theta equal to 180 degree, equal root over vg square. Mod minus v means v square, v only, v square, plus 2 vg v, mod minus vector v means only v, cos 180 degree minus theta, where theta is the angle between the direction of vg and v. Root over vg square plus v square, or v square plus vg square minus 2 v vg cos theta. because cos 180 degree minus theta is minus cos theta, equal root over v square plus vg square minus 2v vg cos 180 degree. Theta is 180 degree and cos 180 degree is minus 1. So what we can write, root over v square plus vg square, v square plus vg square plus 2v vg. Therefore, u equal v plus vg. U equal v plus vg. That is the relative velocity of exhaust gases with respect to the rocket. U equal v plus vg. But considering the opposite direction of exhaust gases and the rocket, here we can write u equal minus v plus vg. Negative sign indicates that the exhaust gases are ejected in the opposite direction with respect to the direction of motion of the rocket. But as the exhaust gases and the rocket are moving in the opposite direction, are moving in the opposite directions, comma, we can write u equal minus v plus vg. U equal minus minus v plus vg. U is the relative velocity of exhaust gases with respect to rocket. So u equal minus v plus vg, which is equation 3. And the negative sign indicates that this negative sign means u equal minus v plus vg. This negative sign in the expression of u indicates that, or is for the downward direction of motion of the rocket. This negative sign is for the downward direction of motion of the rocket, motion of the exhaust gases. This negative sign is for the downward direction of motion of the exhaust gases. In contrast to the upward motion, of the rocket. Upward direction of motion of the rocket. Upward direction of motion of the rocket. This is equation 3. U equal minus bracket open v plus vg bracket closed. Putting this value of u from equation 3 into equation 2, putting the value of u means relative velocity of exhaust gases, putting the value of v plus vg from equation 3 to equation 2, equation 3 to the equation into in the equation, putting the value of v plus vg from the equation 3 in equation 2, we get equation 2 was dv equal minus v plus vg by a plus v plus vg divided by m into dm. So dv equal minus, now dv was v plus vg divided by m into dm. Therefore dv equal minus u by m, where u is a relative velocity of exhaust gases with the rocket with respect to the rocket, into dm. dv equal minus u by m into dm. This is the corresponding increase in velocity of the rocket due to ejection of exhaust gases. Here, mass of the rocket decreases, but velocity increases by keeping linear momentum of the rocket constant. In this case, principle of linear momentum of the rocket is obeyed. That means linear momentum is conserved. This is the increase in velocity of the rocket. Increase in velocity of the rocket. Now we can find this is the increase in velocity of the rocket in small interval of time dt. In a small interval of time dt. So now we can find the expression of acceleration of the rocket. Therefore, the upward acceleration of the rocket, upward acceleration of the rocket upward acceleration of the rocket is given by a equal rate of change in velocity, that is dv by dt. Now putting the expression of dv here, we get minus u by m, relative velocity of exhaust gases divided by final mass of the rocket, minus u by m into dm dt. So this is the expression of upward acceleration of the rocket. A equal minus u by m dm by dt, where m is the final mass of the rocket and dm by dt is rate of ejection of exhaust gases, or rate of decrease in mass of the rocket, where a is much greater than g. In that case, the expression of upward acceleration of the rocket is a equal minus u by m dm by dt. This is the upward acceleration. This is the upward acceleration of the rocket. Due to ejection of exhaust gases. Due to ejection of exhaust gases. Of mass dm in small interval of time dt. In the small interval of time dt. Hence, dm by dt is rate of ejection of exhaust gases. And in practical, in the expression of A, which is minus u by m dm by dt, numerical value of dm by dt will be negative. That's why acceleration will be positive. A will be positive. Final velocity of the rocket. Final velocity of the rocket. Now we can find the expression of final velocity of the rocket. The expression of A was equation 5. Now we have to find the final velocity of the rocket. Final velocity of the rocket. We know the expression of increase in velocity of the rocket, which is dv equal now we can draw the diagram again. This is the diagram of a rocket. We can draw two stages of a rocket. Initially, the rocket is moving same rocket at instant t plus dt. M0 is the initial mass of the rocket at instant t equal to 0. Rocket was moving with velocity v0 in vertically upward direction, and m is the reduced mass of the rocket after ejection of exhaust gases, and velocity of the rocket increases to v, and this is the exhaust gases which are ejected with velocity vgi at instant t equal to t. Now we know that the corresponding increase in velocity of the rocket in small interval of time dt is dv. From equation 2, if we check the equation 2, from equation 4, dv equal minus u by m into dt into dm. dv equal minus u by m into dm, which is the increase in velocity of the rocket. Integrating both sides, we get integrating both sides, we get integration dv equal integration v0 to v dv equal integration minus u by m dm, and it is integrated over dm means over mass. That's why you have to use lower limit of mass, that is m0 to m, m0 to m, or comma integration dv means only v under third bracket v0 to v equal minus u is constant, that is relative velocity of exhaust gases is constant with respect to the rocket, equal minus u integration m0 to m dm by m, or comma v minus v0 equal minus u log base e under third bracket log m base e m0 to m equal, or comma v minus v0 equal minus u under bracket log base e m minus log base e m0, putting upper limit first, then to that is putting m in place of m, then putting lower limit in place of m means putting m0 in place of m. V minus v0 equal u log m0 minus log m, log base e m0 or log m0 base e minus log m base e, or comma v minus v0 equal u log base e under bracket m0 by m, using the formula of logarithm, that is log a minus log b is log a by b. Therefore, if v equal v0 plus u log base e m0 by m. This is the final velocity of the rocket at instant t equal to t, that is v equal v0 plus u log base e m0 by m, where v0 is the initial velocity of the rocket in vertically upward direction, u is the relative velocity of exhaust gases in vertically downward direction, m0 is the initial mass of the rocket, and m is the final mass of the rocket. Log base e m0 by m means log base c initial mass by final mass. This is the final velocity of the rocket at the instant t equal to t, at the instant of time t equal t. If v0 is 0, when where v0 is the initial velocity of the rocket, and u is the relative velocity of u is the relative velocity of the exhaust gases with respect to the rocket. If v0 equals 0, that means rocket starts its motion from rest. In that case, v equal to u log base c m0 by m. Therefore, v equal u log base c initial mass by final mass. v equal u log base c initial mass of the rocket divided by final mass of the rocket. Here initial mass is greater than the final mass of the rocket because exhaust gases are ejected from the rocket and mass of the rocket decreases to m from m0. v equal u log base c initial mass of rocket divided by final mass of the rocket. That is the final formula of final velocity of the rocket, v equal u log base c m0 by m. Also, thrust acting on the rocket, due to which the rocket is moving upwards, thrust on the rocket is given by F equal mass into acceleration. Thrust is equivalent to force acted on the rocket in a vertically upward direction is F, which is ma equal m under bracket minus u by m dm by dt. So finally we get the expression of thrust acting on the rocket, which is F equal to minus u dm by dt, where u is the relative velocity of exhaust gases with respect to rocket and dm is the rate of ejection of exhaust gases. So for a numerical problem, dm by dt should be taken as negative so that thrust on the rocket will be positive. Where dm by dt is the rate of ejection of exhaust gases from the rocket. Which will be assumed as negative for numerical problem in the expression of force F. So F equal to minus u dm by dt.